All right, today we're going to put on our detective hats. We're diving into the world of data, all that messy, random looking information that's all around us. And we're going to learn how to turn it into something that actually makes sense, something that can even help us predict the future. So let's get into it. When you first glance at a bunch of raw numbers, maybe it's your daily screen time or the price of coffee every day, it can just look like total chaos, a big jumble of noise. And it makes you wonder, is any of it meaningful or is it all just random? Well, what if I told you that buried inside that mess, there are actually hidden stories? Patterns just waiting for someone, like you, to find them with the right tools. That's really the big idea for today, finding the meaning hidden in the mess. Now, to solve any mystery, you need a plan, a method. And in our case, that method is called data modeling. You can just think of it as our official detective's playbook for sifting through the clues and figuring out what's really going on. So what does this detective work actually look like? Well, it's basically a four-step investigation. First, you show up and you collect the clues. That's your data. Then you got to organize it all, summarize it, so you can actually see what you're working with. Next, you start connecting the dots, spotting those hidden patterns. And finally, this is the really cool part. You use those patterns to make a prediction, an educated guess about what's going to happen next. Every good detective has a toolkit, right? And for us, the very first tool is learning how to identify our clues. Because in the world of data, our clues really only come in two main flavors. So on one side, you've got discrete data. These are the things you can count. 1, 2, 3, 4, like the number of people in a room. They're whole, separate numbers. And on the other side, you've got continuous data. These are things you measure, like how tall someone is or the temperature outside. It can be any value within a range. So, for example, the number of students in a class or what you roll on a pair of dice, that's discrete. I mean, you can't have 3.5 students, right? But things like height, temperature, or the time it takes you to get to work, that's all continuous. Getting this difference down is absolutely key because it tells us which tools to use later in our investigation. Okay, now for a bit of a plot twist. One of the most common tools we all use, probably the first thing we learn in math class, is the average, or the mean. But here's the secret. Sometimes this clue can be a total liar. It can mislead you and send your whole investigation down the wrong path. Let's open up a case file. Here we've got 6 test scores from a class. Now just look at them for a second. Most of them seem kind of clustered together, right? But there's one that really stands out. And there it is. Our prime suspect, that score of 90. In data speak, we call this an outlier. And it's so different from the rest that it has the power to completely twist the story of how this class actually did. Let me show you how. If we calculate the mean average, add them all up and divide by 6, we get about 56.7. See what happened? That one stellar score of 90 dragged the whole average way up. It makes it seem like the typical student did much better than they really did. But if we look at the median instead, that's just the number smack in the middle if you line them all up, we get 51. Now that feels a lot closer to the real story, doesn't it? So here is the golden rule, and this is a big one for any data detective. When your data is skewed by an outlier, the median is almost always the more trustworthy witness. It tells you what's typical without getting fooled by the extremes. So far, we've just been looking at clues from the past, right? Figuring out what already happened. But the real goal, the real magic of being a data detective is using that evidence to predict what might happen in the future. This is where we go from being historians to being fortune tellers. Well, sort of. And for that, we use a tool called empirical probability. Now, it sounds fancy, but the idea is incredibly simple. It just means we figure out how likely something is based on what's already happened. It's all based on real-world evidence. The formula is right there. You just take the number of times something happened and divide it by the total number of times you checked. That's it. Let's make this super simple. Imagine we tracked the weather for 200 days and it rained on 50 of those days. Okay, so the empirical probability of rain is just 50 divided by 200. That gives us 0.25, or a 25% chance. And just like that, we've turned past observations into a pretty reasonable forecast. This basic idea is how everything from your insurance rates to sports betting odds gets calculated. It's all about using the past to predict the future. All right, it's time to put all of our new detective skills to the test. We're going to solve one last case together. The timeless classic mystery of the late bus. So here's our evidence log. For 7 days, we tracked how many minutes late the bus was. And just like with our test scores, you can probably already spot our prime suspect, that big 15-minute delay. So, to crack this case, we're going to follow our proven 3-step investigation. First, we summarize the clues. Second, we interpret what they're telling us. And third, we make our prediction. Let's do it. Step 1. Summarize the clues. The mean, or the average lateness, is about 3.4 minutes. But again, that number is lying to us a little bit, isn't it? It's being pulled way up by that one really bad day. The median, though, our trusty witness, tells us the middle value is just 2 minutes. That's a much better picture of a typical day. So, step 2, what does this actually mean? Well, it tells us that on a normal day, this bus is late by somewhere between 0 and 3 minutes. That 15-minute delay, that was a fluke, a one-off. It was not the rule. This is so important because it means a model built around the median of 2 minutes gives us a much more realistic expectation for our morning commute. And that brings us to the final step, the prediction. Based on our evidence, what's the probability that the bus will arrive within its normal window? 3 minutes late or less. Well, that happened on 6 of the 7 days we watched it. So the probability is 6 out of 7. Case closed. So there you have it. You've now got the basic skills of a data detective. But before I send you out into the world, let's go over a few key rules to keep in your handbook so you don't make some common mistakes. First, and I can't say this enough, always check for outliers before you trust the mean average. A single weird number can throw everything off, so always compare the mean and the median to get the full story. Second, be careful about making huge predictions from a tiny bit of data. Our 7-day bus example was great for learning, but in the real world, you'd want a lot more evidence. And finally, just remember that our models all work on one big assumption, that the future is going to look a lot like the past. Our bus model is great, right up until they start major road construction on the route. When the world changes, your model has to change with it. So we've gone all the way from a confusing mess of numbers to a meaningful model that can actually help you make better decisions. And I'll leave you with this final thought. What messy data in your own life, from how long your meetings run to how well you sleep at night, is just sitting there, waiting for a data detective like you to come along and find the hidden pattern? Thanks for joining me. Hey there, and welcome. So today we're going to learn a new language. And no, I'm not talking about Spanish or Japanese. I'm talking about the language of mathematical translation. It's this amazing skill, really, that lets you take these messy real-world stories and turn them into clean problems you can actually solve. Let's dive right in. Okay, so take a look at this. I'm sure you've seen something like this before, right? It's a classic. Feels more like a riddle than a math problem, you know? You've got one thing working against another. And just looking at it, the answer isn't exactly jumping off the page. This right here, this is our real-world story, and our mission, it's to translate it. And really, that's the whole game right there. See, real life is all about stories. Cars moving, time passing, things happening. But math? Math speaks a totally different language. It's all about numbers, symbols, and these nice, neat equations. Mathematical modeling is basically being the translator between those two worlds. It's the art of turning one into the other. Now, I know what you might be thinking. This translation thing sounds like some kind of high-level magic trick, something only geniuses can do. But I promise you, it's not. It's actually just a process, a super simple, repeatable 4-step cycle that, honestly, anyone can learn. And it'll help you to code pretty much any problem that comes your way. And here it is, the mathematical modeling cycle. Seriously, think of this thing as your personal Rosetta Stone for solving problems. It's just 4 steps. Step 1, understand the real problem. Really get the story. Step 2, build a mathematical model. That's our translation part. 3, solve the model. Do the math. And finally, step 4, interpret your answer and check it. It's this little loop that just keeps you on track every single time. All right, enough talk. Let's put this cycle to work. We're going to grab that leaky tank problem we started with and walk it through our 4-step process, step by step. Okay, step 1. And honestly, this is the most important one. Just understand the problem. Forget the numbers for a second. What's actually going on here? We've got water coming in, and we've got water going out at the same time. What we're really looking for is the net effect of those two things happening together. So the key concepts we got to nail down are the filling rate, the emptying rate, and what happens when you put them together.
And this is exactly why that first step is so crucial. A lot of the time, the hard part of a problem isn't the math itself, it's figuring out what the heck you're supposed to be doing in the first place. The real secret, the key idea, it's almost always buried in the words of the story, not the numbers.
All right, on to step 2. Let's build a model. This is where we do the translation. We start defining things in math terms. So let's say the entire tank is just 1 unit. That's the whole job. So the fill rate, that's 1/4 of the tank per hour. And the empty rate is 1/6 of the tank per hour. Now here's a really important part. We have to make an assumption. We're going to assume those rates are constant. This is how we take a messy real-world situation and simplify it just enough so we can actually solve it. And this is what's so cool about it. The whole drama of the tank filling up and draining out, it all boils down to this one super clean equation. The net rate is just the fill rate minus the empty rate. Simple as that. That's our model. Step 3. And honestly, this is usually the easy part. We've already done the heavy lifting with the translation. Now, we just have to do the arithmetic. So we find a common denominator, and boom. We see the net rate is 1/12. That means the tank is filling up by 1/12 of its total size every single hour. So let's think about that. If it's filling up by 1/12 every hour, how long is it going to take to fill the whole thing? You got it, 12 hours. That's the answer our model spits out. But wait, we're not done yet. This last step is absolutely critical. We have to interpret the result. We translate that number, 12, back into the story and ask ourselves, does this even make sense? Let's see. It takes 4 hours to fill it with no leak, so with a tap draining it, it's got to take longer, right? 12 hours sounds pretty reasonable. It passes the gut check. So our model is good to go. And here's the beautiful thing about this cycle. It's not just for problems about leaky tanks. It's super versatile. So let's take the exact same 4-step process and apply it to a totally different kind of problem. This time with geometry. Okay, here's the news story. Imagine you've got 60 meters of fencing. That's it. And your job is to build a rectangular field that has the biggest possible area. So the question is, what dimensions do you need to make that happen? So we just follow the cycle. We understand the problem, right? Now let's build our model. If we call one side x, then the other side has to be 30 minus x to make the perimeter 60. And just like that, we can write out the whole area using this one elegant little equation. See that? That is the mathematical model of our field. And when you solve that model, you find that the biggest area happens when x is 15. What does that mean? It means the perfect shape is a square, a 15 by 15 meter square. And when we interpret that, it just kind of feels right, doesn't it? It totally matches our intuition. So by now, you've seen just how powerful this cycle can be. But, becoming a really good translator also means knowing what not to do. There are a few common mistakes, little traps that can really mess you up. And these are the big ones, the classic errors. Jumping straight to the math without really getting the story first. Or, and this is a big one, forgetting to check if your answer is totally crazy, like getting -5 hours as an answer. And, of course, making things way more complicated than they need to be. Just remember, the goal here is always clarity and simplicity. So, what's the big takeaway from all this? It's that mathematical modeling isn't just about solving homework problems. It's a whole new way of thinking. It's like learning a new language that lets you see the world with so much more clarity. You've basically just learned the basic grammar of that language. So the only question left for you is, what problem in your world are you going to translate next?